Alright, so hopefully everybody has their PowerPoint out. This is 6.1 Introduction to Probability. You know, we use probabilities every day. Even though you don't think you do, you do. If you think about a lot of people are concerned whether it's going to rain or not, right? So, you know, that's really that percentage. That's really just a probability. It's not a for certain thing. You know, if there's a 60% chance that it's going to rain today, then that means that it's a 40% chance that it's not going to rain today, right? So we use probability all the time. If you like to gamble, which I'm not saying that I'm for or against, but I don't like losing my money. But if you do, I mean, all of the games in the casino, they run off of probability. There are some games that, if you follow certain rules, that you are more likely to win than others. I've always heard that one of the best games to play, the best odds you would get, or odds of winning, would be either betting, in this course this doesn't take any skill into account, would be betting on either red or black on the roulette wheel. Now, it's not a 50-50 chance of winning, because usually there's a 0 and a double 0 on the roulette wheel. So that's not red or black. But it's a little bit less than 50% chance of winning. If you just want to go off a chance, that's your best bet. But then you got games that require skill, and some people can count cards and do all that, so they can do all the probabilities in your head. Like all these people, if you ever watch the poker series or anything, they're running probabilities in their head to try to figure out if they want to, you know, bet or whatever, go to the next round of the poker game or whatever. So probabilities are used a lot, not only in gambling, but that is one place where they're handy. So with probability, we have a bunch of different definitions that we're going to use going forward. One is what an experiment is, or a random experiment. A random experiment is defined as any activity or phenomenon that meets the following conditions, and this is in your PowerPoint. There is one distinct outcome for each trial of the experiment. The outcome of the experiment is uncertain, and the set of all distinct outcomes of the experiment can be specified and is called the sample space, denoted S. So, what is a sample space? That's all the possible outcomes. And I used a word that I haven't used yet, which is outcome. But sample space is all of the distinct outcomes of an experiment. So if I was to flip a coin one time, then the sample space would be equal to heads or heads and tails. All right, and of course that's if it's a fair coin. It's not weighted on one side or anything like that. But that's the sample space. If I was to flip a coin two times, then my sample space would be heads. Well, let's just use H for heads. So it would be heads, 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 tails, tails, heads, or tails, tails. So all the possible outcomes. And an outcome is any member of the sample space. That's in your PowerPoint as well. So any member of the sample space is an outcome. So what's the sample space for, let's say that we had, that I know I'm going to have 3 children. When I grow up and get married, or maybe I'm already grown, when I get married and I decide to have kids, I'm going to have 3 children. Okay? What's the sample space if having a boy and a girl is equally likely? What's the sample space for having 3 children? Okay? So the sample space would be girl, 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 boy, girl, boy, girl. What else? Girl, boy, boy. You have boy, 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 girl, boy, boy, girl, girl. There's one more. What is it? What is it? Boy, boy, girl. All right, so that's the sample space. There's no other way to have 3 children. Okay. Another thing that we're going to have to understand to work some of these probability problems is a standard deck of cards. And some people have never played cards or really know that much about cards. If we have a standard deck of cards, I don't think this may or may not be, it's not in the PowerPoint. All right, so what's a couple of things we know about a standard deck of cards? How many cards are in a deck? A standard deck? 52, right? So we know that we have 52 cards in a standard deck. Okay, we also have something called suits in a deck. So we have 4 suits in a deck. What are the 4 suits? Hearts. So we have 13 hearts. We have 13 clubs. We have 13 diamonds. And we have 13 spades. All right. The hearts and the diamonds are both red suits. Okay, so you may want to, if you don't know that, you might want to write that down. They're both red suits. Okay. The clubs and the spades, they're both black suits. All right, so in each suit, so in every suit, we don't have a 1. All right, we have, so the sample space for each one. So this would be, 4 sample spaces, but for each one, we'll have, ooh, that's a bad bracket there. A 2, 3, 4, 5, 6, 7, 8, 9, 10. We will have a jack. We'll have a queen, a king, and an ace. All right. Can anybody think of anything else about cards? Yeah, I don't think we have to worry about the jokers unless it tells us that the deck has jokers. Face cards. What are the face cards? Anybody know what the face cards of a deck of cards is? Here. Some people consider the ace to be a face card because I've seen aces drawn with like a little face on it or something. But in a standard deck, we have 3 face cards in each suit. So these 3, the jack, the queen, and the king, are considered to be face cards. And they're called face cards because usually they will have a jack picture, a queen picture, and a king picture on those. So how many face cards are there total in a deck of cards? 12, right? 4 times 3, or 12 face cards. And the reason, and I know a lot of you know a lot about cards because you play all the time, but then there's a couple that may not have played cards that much growing up. I just want to kind of clarify a couple of things about cards. See if I can find a picture of a face card for those of you who haven't seen, which would be pretty tough to not have seen, but here are some face cards right here. All right. And some of the problems that we work is talk about cards. And if you don't know what I'm talking about, then I don't want that to be the part that's giving you issues, you know. Anyway. All right, so we have a couple of different approaches that we can use when trying to figure out the probability of something. One of those approaches is called the relative frequency approach. All right, and so with the relative frequency approach, your book says if an experiment is performed n times under identical conditions and the event A happens k times, the relative frequency of A is given by the following expression. So it says the relative frequency of A is equal to k divided by n, where k is the number of times that event A happens, and n is the number of times that the experiment was repeated. All right, so if the relative frequency converges as n increases, then the relative frequency is said to be the probability of A. K is the number of times that an event happens. And N is the number of times the experiment is performed. So if you flip a coin 10 times, and we want to know the probability that it lands on heads. Well, we all know that the probability is 1/2 because there's only 2 outcomes. But if I flip it 10 times, what if I only get 3 heads and I get 7 tails? Does that mean the probability is 3 out of 10 of getting a heads? No. But as I increase the number of times I flip the coin. So what if I didn't flip it 10 times? What if I flip the coin 10,000 times? It'd take a little while. You know, I'd probably get tired, have to take a break. But the fraction that we would get if I flip the coin 10 times would actually be approaching, it may not be exactly 1/2, but I bet you it would be really close. All right? It might be 0.4999, it may be 0.50001. It may not be that close at all, but it'll be close. It'll be close to 0.5 or close to 1/2. All right, so that's a relative frequency approach. You repeat the experiment over and over and over and over and over until you get a value that your fraction is getting around. If that makes sense. You get a number that your fraction is getting close to. So here is, and this I don't think is in your PowerPoint. It's just something cool to look at. So let's see. Here is the relative frequency of heads for 42 flips. So they flipped this coin 42 times, and they're showing the relative frequency using that formula. They're showing it. Of course, if you flip it one time, 1 over 1 is 1.00. All right. But then you can see as they flip the coin, the probability changing, the relative frequency changing. All right, and so we go down to the 42nd time. So even flipping the coin 42 times, it only came up on heads. That will be 35.71% of the time. But we all know it's 0.5. Well, it could just be that it landed on tails more than it did heads. But if I was to flip this coin 42,000 times, 100,000 times, then you would get to the relative, you'd get to the actual probability. One time when I was taking a statistics class, when I was at Mississippi State, I was working a probability problem, and I couldn't get the right answer because I wasn't working it the right way. I knew the answer I was getting could not be right. And I knew what, I had a guess of what the actual answer could be. So what I did, I'd taken a couple programming classes back then. I wrote a little program that would repeat that experiment 100,000 times. Because I couldn't repeat the experiment 100,000 times. And so what that did was, that relative frequency that I got was the answer I knew it should be, but I had no idea how to do it. So, and it was like a take-home something that we had to turn in. So I just printed out my program, and I told him, I was like, I can't figure out how to work this, but here's the program to do it, and here's the answer I should get. He gave me partial credit, so it wasn't too bad. But if you can repeat the experiment over and over and over and over and over, then eventually your relative frequency will approach the actual probability. All right. Here is a scatter plot. Let's look at these scatter plots of flipping the coin and the number of heads. All right, so this top one here is the 42 flips. And here's 0.5. Here's what we know it should be. You know, we all know it's a 1/2, hopefully. You've seen, you know, it's a 1 out of 2 chance, or 0.5. So this was the 42, and you saw it really didn't look like it was approaching this 0.5. Here's flips 200 through 300, so you can see it's getting closer to the actual line here of 0.5. And then here's flips 1,350 to 1,450, and you can see that you could almost draw a straight line. It's not exactly a straight line, but you can almost draw a straight line across at 0.5. All right, that's kind of neat. Not really neat, but kind of neat. All right, what if let me ask you this, just to see what you think. What if I flipped a coin 10 times and I got 10 heads? What do you think the probability of me getting a head on the 11th flip is? It's 1/2. It doesn't matter how many heads or how many tails I've gotten in the past. It's still going to be 1/2. Now, if I ask you the question, what's the probability of me flipping a coin 11 times and getting 11 heads? It will be 1/2 to the 11th power. Ugh, that's a really small chance. All right, the other approach is the classical approach. Okay, this approach is where you simply take the number of outcomes, so how many times it happens in the sample space, divided by the number of possible outcomes. All right, if you look on your PowerPoint on the back of the first page, which would be page 2, you look in the top right-hand corner. This is where we start going over the classical approach, and it says, and look at the notation that's used for the probability of an event A happening. The probability of A. This means the probability of event A. That would be equal to, it says, the number of outcomes in A divided by the total number of outcomes in the sample space. All right, so if I want to know the probability of flipping a coin once and getting a head, then there is one of the two. Remember, our sample space for flipping a coin was just heads and tails if we flip it one time. So the probability of flipping a coin and getting a head would be there's one chance and there's two outcomes. So it'd be 1/2. All right. The next, the problem here in your PowerPoint is similar to the sample space here is similar to the sample space of having 3 children. This problem says, what if I flipped a coin 3 times? Right, so there's a 1 out of 2 chance of having a boy or a girl. I believe it's actually a little different, but for simplistic sake, we'll say it's equally likely. It's the same for heads and tails. All right. So it says a coin was tossed 3 times, and the number of heads was observed. The sample space consists of 8 outcomes. Let A be the event of getting at least 1 head. What is the probability of A? So what we're looking for is the probability of at least 1 head. So at least 1 means I could get 1, I could get 2, or I could get 3, right? At least 1. So count up the number of sample space, the number of outcomes there that have at least 1 head. How many? At least 1 head. 7. How many total outcomes are there? 8. There is the probability of getting at least 1 head if you flip a coin 3 times. 7 out of 8. So that can be written as a decimal. That's 0.875, which then could be written as a percentage if I wanted to. That's 87.5%. Most of the time, I guess, for these probabilities, we'll leave it as a fraction or decimal. All right, does everyone know what a die is? I'm not asking you to die. Stay healthy, live long, and prosper. A die is a single, if we have a pair of dice, D-I-C-E, a die is one of those dice. Now, if you have played Dungeons and Dragons or something like that, you may be used to dice that have multiple sides, maybe a 10-sided die or 12-sided die or something like that. But in general, if we talk about a die, that is a single die, then it will have how many sides? 6, right? Yeah, 6. So for a die, and it is D-I-E, die, our sample space is equal to, and this is just a, I guess a standard die, would be 1, 2, 3, 4, 5, or 6. So there's all kinds of problems that I could come up with, or that we could have if we rolled a die. Then what's the probability that I roll a 5? Well, using the classical approach, there is one outcome that's 5, and then there are 6 possible outcomes, so it would be 1 out of 6, or 1/6. All right. What is the probability of rolling an odd number? How many of these numbers are odd? 3. How many numbers do we have? 6. 3 out of 6 is 1/2. Okay. What about if I had a standard deck of cards? What is the probability of, if I draw one card, getting a jack? Alright, so how many cards are there? That'll be our bottle number. 52. How many jacks are there going to be in the deck? There's one jack in each suit. So there are 4. So the probability, if I draw a random card out of the deck of getting a jack, is 4 out of 52, or 1 out of 13. That's the classical approach. Does that make sense? I mean, it's probably things that you understand, that you've seen before. Another way to figure out the sample space, because sample spaces can get pretty complex. Especially, okay, it's not too complex if I just flip a coin once or twice or 3 times. What about 4 times or 5 times or 6 times? So it gets pretty complex. If you ever are having trouble figuring out a sample space for an experiment that's done multiple times, one way of figuring out that sample space is by doing a tree diagram. Now, I don't think this is in the book. You don't have to write this down, but just know this is in your book. And this is a tree diagram that would give you the sample space for flipping a coin 3 times. I can remember first seeing this. I'd never seen it in college until I got to Mississippi State, seeing this tree diagram. And it really didn't make that much sense at first. The more I looked at it, the more sense it made. So what it means is, I'm going to scroll it down a little bit so I can come to the board. So here's our first flip of the coin. Like if we get a heads the first time, then on the second flip of the coin, I'm either going to get heads or tails. Well then, depending on which one of those I get, I'll get heads or tails. So if you trace this, heads, 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 that gives you that sample, or that event, I guess you could say, that item in the sample space. And you can trace each one once you do your entire tree. All right. So that might help you with sample spaces if your sample space is large. Even if it's just 3, you might not be able to figure one out. Maybe one's not coming to you. You can do a tree diagram like that. And that may help you. All right. So your book goes through, it says the subjective approach, which wouldn't be a very good approach, I wouldn't think. It says the subjective viewpoint regards the probability of an event as a measure of the degree of belief that the event will occur or will not occur. Someone's degree of belief in some event will depend on his or her life experiences. Different life experiences produce different degrees of belief. So I don't think the subjective approach would be that great. But, if you are working on something and you're working with a guy that's been doing it his whole life and he says, hey, don't do this, or this might happen. It doesn't always happen, but it might happen. You might get electrocuted if you do that. You should probably listen to them. Okay? So, but in general, the subjective approach is not very good. Most of the time, when we work with samples, what we're trying to do is deduce from the samples the population parameters, like the means, the proportions, the variances, things like that, of different variables. So if we are looking at means, proportions, variances of a sample, then those population parameters, if we're working with those, and we're trying to make judgments or we're trying to make predictions, that's called statistical inference. So that's on your PowerPoint. It's the last definition. It says statistical inference involves the use of sample data to form generalizations or inferences about a population. Using sample data to estimate the values of population parameters is one form of statistical inference. And that is the first section, 6.1. All right, 6.2, we're actually going to get to do a little math, a little more math. Addition rules for probability. So, interpreting the probabilities using that classical approach is the best way. Okay, that's a very good way of thinking about the basic probability principles. Okay, so we are now going to go over some rules, just some basic probability rules or laws. We don't want to break the law. Don't break the probability law. That will always be true. Okay. A probability of 0. That means the event cannot happen. So the probability is going to be 0 when an event cannot happen. So what's the probability that we will not have homework on this section? It's 0. Now whether you do it or not, that's up to you. But the probability that we will not have homework is 0. I can guarantee you. All right. A probability of 1 means the event must happen. So the probability that today is Tuesday is 1 because today is Tuesday. The probability that the sun is going to rise in the morning, I would say it's 1. I guess, well, I don't know. Maybe, maybe not. But it's very close to 1. All right, so all probabilities, every probability that we come up with has to be greater than or equal to 0 and less than or equal to 1. So you cannot have a probability greater than 1, and you cannot have a negative probability. So your book says all probabilities must be between 0 and 1 inclusively. The closer the probability is to 1, the more likely the event is to occur. The closer the probability is to 0, the less likely the event is to occur. So, I mean, these are all in your PowerPoint if you're wondering. Now, if you have a bunch of different events, let's say you have a sample space that has many different outcomes, the sum of all of the probabilities of the outcomes is equal to 1. So the sum of the probabilities of all outcomes must equal 1. We have to use this fact. This is a very, very powerful fact. And sometimes we have to use this fact to help us work out a problem. And actually, it can give us shortcuts to work out a problem by knowing this fact. So there's some probabilities we're going to work. There's a couple different ways you can do it. But if we use this fact, there's sometimes a shorter way to figure out, quicker way to figure out the probability. All right, a compound event. Just what it sounds like. What do you think? All right, that's going to be when you combine 2 or more events. So a compound event has 2 or more events. So for example, I could say if I flip a coin and I pick a random card from a standard deck, what is the probability of getting a heads and a 3 of spades? That's a compound event. Okay, so more than one thing happening. Sometimes doing some basic math, I guess using some basic math knowledge about intersections and unions and things like that can help us figure out. I don't know if you know what a union is. If you've worked with, remember, let's say we're looking at the domain of a function and you had to leave a number out, so then you had to write the intervals on which the function was defined, and you had one ordered pair, and then you'd put a U, that means union with, and then another ordered pair. So sometimes our set of answers can actually overlap, and that's called a union. If you look on the back of your PowerPoint, this will be page 2, you can see it says the union of the events A and B is the set of outcomes that are included in event A or event B or both. Symbolically, the union of A and B is denoted A, U, B. That means A union with B. So if we have, and you can use a Venn diagram, this is what this is called, to explain that. Let's say that we have an event A here, and we have an event B here, right here. That's A union with B. That's where both are occurring. Okay. So that's A union B. All right, if we want to look at and I said both are occurring, look at the definition. The union of events A and B is a set of outcomes that are included in event A or event B or both. So it is where they overlap or where they are in the different sets. That's the union. The intersection, so this actually goes everywhere. The intersection is written like this. It's the upside down U. I mean, you could say it kind of looks like an N, but it's probably better to think of it as the upside down U. The intersection is the actual place where the two intersect. So if I drew event A and event B, there's the intersection. So the union is everything. The intersection is just this part. Now this next one that I'm about to write up here, we use this a lot in probability. It's going to be used throughout the rest of the semester because we can actually use some of these probabilities. We can figure out different statistics using the probabilities, and so we have to use this next term a lot to speed things up, and it is the complement. And the complement of an event is everything that is not in A. I usually write it like this. Your book writes it like this. I guess the C stands for complement. But if you needed a Venn diagram to show you that, if this is A, if this is everything that can happen in event A, then everything that couldn't happen would be on the outside. Now, what do you think that the probability of something happening plus the probability of something not happening has to be equal to? 1. So the probability that it will rain today or will not rain today is 1. There's a 100% chance that it will rain today or it will not rain today. All right, so complement is used. How else could the complement be used? Well, if I know the probability of something occurring plus it not occurring has to be equal to 1, then I know that the probability of something happening or occurring is equal to 1 minus the probability that it doesn't occur. Just moving that variable over. Moving the probability of not A to the right side of the equation, I know that the probability of something happening is equal to 1 minus the probability of it not happening. All right, these two facts are used a lot in statistics and in probability. All right, if that's true, what's one other statement I could write that would make sense? If the probability of something happening is equal to 1 minus the probability of it not happening, the probability of something happening plus the probability of it not happening is equal to 1, then what would the probability of it not happening be equal to? What's another statement I could write? 1 minus the probability of it happening. So if I told you there was a 60% chance that it was going to rain today, and you needed, and I know that you can figure out the probability it's not going to rain probably in your head, but what are you doing? You're saying 100% minus the probability that it would rain. So if I tell you there's a 60% chance that it will rain today, then in your mind you probably automatically would think 100% minus 60% equals 40%. And that's the chance of it not raining today. Now, with percentages, you can always change that over to decimals and whole numbers. And the biggest whole number you would have is 1, right? All right, let's look at this problem. Alright, it says consider the event A equals annual income is greater than $50,000. Alright, suppose the probability of A is 0.08. So they're saying that 8% chance that annual income is greater than $50,000. Determine the probability of observing someone whose income is less than or equal to into $50,000. Let me read that again. Determine the probability of observing someone whose income is less than or equal to $50,000. So if you know that the probability that someone's income is going to be greater than $50,000 is 0.08, then the probability of not occurring is 1 minus 0.08. or 0.92. So in this particular problem, the probability of the annual income being less than or equal to $50,000 is 0.92. All right, odds. You ever heard of odds? Like the odds of something happening. That's a little bit different than probability. Even though some people get confused, odds are a little different. Alright, odds, and this is at the bottom of page 3 of your PowerPoint. The odds in favor is equal to the probability of A divided by the probability of not A, or its complement. That is the odds in favor. And usually we don't divide those like that. We will write it down like that, but then we have to write our answer a different way, and I'll show you in a second. So that's odds in favor, and odds against is equal to the probability of not A over the probability of A. So if I know the probability of something occurring, here's a little example. Let's say the probability of some event occurring is 0.3. So then the probability of it not occurring would be what? One minus 0.3, 0.7. So if I wanted to know the odds in favor of this thing occurring, it would be 0.3 over 0.7. Now, I'm not going to leave my fraction like that. How many fractions have you seen left like that in your life? Probably not many. How can I write this in a way so that I can simplify? What does 3/10 mean? 3/10, right? And what does 7/10 mean? 7/10. So if I flip and multiply this, that would be 10 over 7. The 10s would cancel out, and I would be left with 3 over 7. Now that does not mean that the odds in favor is 3/7, even though you would think that. The odds in favor would be, you could see it written two ways. Either you could see it written 3 and then a colon and a 7, or in words what that means is, anybody know? 3, 2, 7. So these two things are read the same way. It's just two different ways to write it. So even though we treat this as a fraction, we don't leave our answer as a fraction if we're talking about odds. You know, you've seen like a horse has a 3-to-1 odds chance of winning. Well, as a fraction, that might not be the same as actually writing 3, 2, 1. All right. All right. Now, here's a problem. Okay. Let's work. Let's see if it's in your PowerPoint. All right, it is. So look on page 4 of your PowerPoint real quick. We're going to read through this together, even though I know you can read. We're going to read through it together. It's page 4, PowerPoint. In the game of American Roulette, the roulette wheel contains numbers 1 through 36. Alternating between red and black. There are 2 green spaces numbered 0 and 00. Does everyone know what the roulette wheel is? It's that wheel that they spin and then they throw a little marble and it goes around and around and around and around and then it lands randomly somewhere. All right? All right, so it says calculate the probability of the roulette ball landing on a red pocket. So this is probability. It says since there are 18 red pockets and 38 possible pockets on which to land, the probability of landing on red is given by 18 over 38. All right, part B says calculate the probability of the roulette ball not landing on a red pocket. So what you can do, instead of counting up everything, all the red, or counting up all the black and the 00s again, you can say 1 minus. So if you say 1 minus the probability of it landing on red, that would give you the probability of it not landing on red. All right, and then C, calculate the odds in favor of the roulette ball landing on red. So you have the probability of it landing on red, that's 18 over 38, divided by the probability of it not landing on red, which was 20 over 38. So we would have to flip and multiply. Those would cancel out. And that would leave me with 18 over 20. That fraction, you can simplify, that's 9 over 10. Now that doesn't mean 9 over 10 like we think about it. All right, the odds in favor then would be 9 to 10. I mean, you can write it as 9 over 10, but it doesn't mean the same as 0.9. You don't think about it that way. All right. So that's the way that odds are different. Now, we can say that two events are mutually exclusive. So two events are mutually exclusive if they have no outcomes in common. So if I was to show a Venn diagram of two events that have nothing in common, it would look like this. They would be separate. So mutually exclusive events do not have anything in common. Mutually exclusivity is also known as disjointedness. It's just another word, disjointedness. You will probably never use that word in the real world. So we can say that these two events are disjointed events. So if the two events are disjointed like that, they're mutually exclusive, then what do you think their intersection would be? What would the probability that both of those things would occur? It would have to be 0, right? Because they don't overlap. All right, the general addition rule, we're finally getting to the addition rule. The probability of the union of A and B. Remember, that's the probability of A or the probability of B or the probability that they intersect. In general, we can write that as the probability of A plus the probability of B minus the probability of their intersection. All right, so you might want to read through that last example there. It's in your PowerPoint. That is a problem that uses the general addition rule, and that is where we will pick up next class meeting.